Hello, everyone. My name is Ruofan, and today I'm gonna present PluS, highly efficient and expandable ML compiler with pluggable graph schedules. And it's a joint work of Renmin University of China, Microsoft, and Tsinghua University. In recent years, we've seen a clear trend of architectural convergence in DNNs. For example, the attention mechanism has become a core building block in state-of-the-art models. But at the same time, this model keeps evolving with new local improvements, like RM as norm for normalization and sweet glue for activation. Besides the trends of model evolving, we're also seeing emerging graph optimization techniques. For example, techniques like flash attention and some fused kernel, like combining layer norm and matmul, are now very common optimizations. All these trends put new demands on ML compilers. We now need more flexibility and extensibility to keep up with both the architectural convergence and rapid kernel-level innovations. ML compilers play a crucial role in turning ML models into efficient executable kernels. Given a DN model, an ML compiler usually lowers it into a computation graph made up of operators. And the typically workflow has two main steps. The first is subgraph identification. For example, the operator fusion where the compiler finds subgraphs that can be optimized together. Then comes the code generation, which generates the actual schedules and kernels for the subgraphs. To handle new expert-driven optimizations like the fused kernel we saw earlier, we can classify the ML compilers into two types, embedded mode and pluggable mode. And this depends on whether they support user-defined functions or not. The embedded compiler builds all the modules inside the compiler itself, so users can't easily customize how they work. For subgraph identification, they mostly rely on the hard-written predefined rules. For example, the TVM groups operators into types like complex out, fusible, injective, and reduction, and then apply some specific fusion rules. But if the users wanted to change these rules, they have to dig into the compiler's implementation, which is not practical. And many ML compilers today follow this embedded mode. And after finding the subgraphs, these compilers lowers the high-level graph down to the hardware code using a low-level IR. And the problem is when we want to adopt new optimizations, it's really hard to change the building graph transformation. It often means putting a lot of efforts to modifying a complex, cumbersome compiler. As a result, the embedded compiler tends to lag behind the state-of-the-art performance. Meanwhile, the pluggable compilers have been developed to let users customize the subgraph identification and code generation. For example, with an existing pluggable compiler like AI template, users can define user-defined patterns during the model setup. AI templates then match the specific operator compositions, like these two Zheng-based subgraphs in the example, and generates code for them. But experts also need to provide the corresponding user-defined schedules and implementations. However, this approach often struggles to support more diverse model architectures. For instance, AI templates support Zheng, bias, and Zhai, but not Zheng and Zhai by default currently. So if you want to drop the bias, you need to add a new backend template and update the frontend too. Also, AI template doesn't yet handle models with dynamic shapes well, which limits its flexibility in broader use cases. So in this work, we introduced PluS, a pluggable compiler that lets experts define the graph transformation flexibly. At the same time, it's a generalized solution that allows different operator compositions to share the same cogent schedule. We observed that the optimized schedule for a subgraph usually depends on the loop structure of its K operator. So our key idea is to use a generalized pattern that captures the fundamental characteristic of subgraphs. This lets us map different operator combinations, like the Zhen by Zhai or Zhen and Zhai into the same representation. To do this, PluS uses a loop-centric subgraph abstraction called PlusGraph. So instead of matching each specific operator composition, it matches a generalized loop pattern. On the other hand, PluS provides an interface called PlusCode that lets users provide cogent templates for each pattern. This template defines the schedule for the loop skeleton of the K operators, like Zhang operation in the example, and the PluS will automatically generate the code for other trivial operation in the subgraph. So this is the system overview of PluS. Initially, PluS built a pattern warehouse to decouple the subgraph identification and code generation from the compiler's internals. In this way, users can manage these processes by providing mappings from the subgraph pattern to their corresponding code templates. And first, PluS takes a data model from a framework and translate it into the computational graph with operators. And each operator is then expressed as a PluS graph. Next, the PluS uses a pattern identification process to find subgraphs that match the patterns stored in the pattern warehouse. Finally, it generates code for these subgraphs using the PluS code templates from the warehouse and automatically fills in the trivial operations to produce the final CODA code. First, let's talk about PluS graph representation. It's a subgraph representation that acts as an identifier for the pattern matching. It has three main features. First, it's lightweight, and because it's designed for the subgraph pattern matching rather than some complex functions. So it should be easy for the ML optimization experts to work with. Second, it encapsulates the key characteristic of the loop and computations. And finally, it guarantees uniqueness, which means each subgraph has its own distinct PluS graph. And a PluS graph consists of multiple levels of PluS loop. Typically, the tensor computation can be expressed as the nested loop, and the PluS loop is our abstraction of each level. And a PluS loop has three main properties: size, parallelism, and operation. And size is just the loop size, and parallelism indicates whether the loop is parallelizable or non-parallelizable. If it's parallelizable, there are no data dependencies, so we can run it in parallel. If not, it needs serial execution or extra synchronization. And the operation is an optional property. It records what the computation happened in that loop. And the compiler will keep all the operations inside that loop, but the users only need to specify the skeleton operator that drives the cogent schedule for the subgraph. For example, a mathmal operation has three loops, M, N, and K, where M and N are parallelizable and the K is non-parallelizable. And the dot operation is in the K loop acts as the skeleton operation. And PluS uses the loop information to identify the subgraph patterns efficiently. To make the PluS graph representation unique for each subgraph, our key idea is to merge the PluS loop as much as possible while keeping the computation correct. This helps simplify the subgraph representation. To do this, we designed three primitives to guide how loops are transformed and merged across different operators when forming a subgraph. The first primitive is merge without altering properties. This means we merge two loops if they have the same size and are both parallelizable. For example, in a mathmal operation with loops M, N, and K, the loop N can be merged with loop N in a following add operation, because the add operation is an injective operation and doesn't change the loop's property. And similarly, we have primitive 2 merge with parallelism modification and primitive 3 transition to a new loop when needed. And after the loops in different operators are transformed, PluS then collapse the consecutive next loop that belong to the same character. Based on the subgraph identifier, PluS uses a pattern matching method to generate subgraph. This process is guided by two key ideas. First, the PluS always starts with a skeleton operator. This is a core operator that decides the data layout and the code gen schedule of a subgraph. Then PluS uses a greedy strategy to expand the subgraph scope and match the largest possible subgraph pattern. Using this workflow, PluS check if the candidate subgraph perfectly or partially match the predefined pattern. And it looks at three loop properties. And if there is a perfect or partial match, PluS keeps expanding. If not, it stops. And we define 4 matching conditions for identifying the partial matches. You can find the details in our paper. In this section, I will explain how PluS generates code for the subgraphs. During the compilation, PluS keeps track all data dependency and operation inside each loops, and this guarantees the correctness and makes code completion possible. To generate the code, experts create a code templates for the skeleton operator using the PluS code interface, and the PluS code covers 3 parts: data placeholder, compute, and writeback. And based on the addressing info, the compiler will automatically generate the code to load input data, perform computations, and write back the result. And PluS also supports dynamic shapes. It does this by using symbolic tabs to represent shape as a compile time, and treating shapes as runtime variables in the code template. And experts can then define shape-based routing in the templates to handle different input size with a dynamic schedule. We implement PluS on top of PyTorch 2, and for our evaluation, we compare PluS with mainstream DNN compilers, including Torch Inductor, TensorRT, and AI Template. We run experiments on 2 different GPUs, an NVIDIA 800 and 409 GPU to cover different hardware architectures. And for models, we test 5 typical DNNs: BERT, LBERT, GPT-2, T5, and VIT. Compared to the state-of-the-art embedded ML compilers, PluS achieves an average 4.4 times speed up over Torch Inductor and 1.77 times over TensorRT. And this shows the advantage of supporting highly optimized subgraph implementation through a flexible, pluggable approach. And in addition, as a pluggable graph transformation solution, PluS delivers comparable end-to-end performance to AI template, even shows an average 7.8% improvement while supporting more model architectures. Next, we present a few case studies to highlight the advantage of PluS. First, we show the subgraph inference latency to demonstrate how PluS can fully leverage efficient subgraph implementations. We also perform an ablation study to analyze why it's necessary to flexible support a variety of subgraph patterns. In addition, we show the portability of PluS compared to AI template and conduct a sensitive analysis to validate its correctness across different settings. To ramp up, we face new challenges today, like convergent model architectures and the rapid evolution of graph optimization techniques. And PluS addresses these challenges by decoupling the graph transformations from the compiler, which helps deploy new optimization more easily and achieves better performance. By using a generic loop-centric pattern matching, PluS can also handle different model variations and keep up with future changes in the DNN design. Thank you for listening. And now I'm currently working on the energy efficiency of ML system with some compiler optimization and kernel level optimization. And I'm happy to connect. Thank you very much. Welcome the questions.